Welcome to This Explainer. Today, we are unpacking something absolutely mind-bending. We're going to dive right into a microscopic breakthrough straight out of Texas A&M University that could, quite literally, alter the entire future of deep space exploration. We're talking about tossing out heavy, volatile rocket fuel and fundamentally changing how we propel objects through space using nothing but the sheer power of light. Let's get right into it. Hundreds of thousands. That massive number is exactly how many years it would take us to reach our nearest star system, Alpha Centauri, if we were using current, state-of-the-art rocket propulsion technology. When you think about space travel in those terms, it honestly feels a bit impossible, right? Hundreds of thousands of years is a timeline that pretty much completely locks us out of interstellar travel. But what if we just threw out the traditional rocket playbook? By utilizing a completely new light-driven approach demonstrated by those Texas A&M engineers, we could slash that unimaginable travel time down to roughly 20 years. Just think about that for a second. We go from a journey that takes hundreds of millennia to a trip you could complete within a single human generation. And the crazy part? This isn't science fiction. It is grounded in real, measurable mechanics. Section 1. Enter the microscopic metajet. So, to figure out how we cross the galaxy in decades instead of millennia, we actually have to shrink our focus way, way down. Let's zoom out of the vastness of the galaxy and straight into the lab for advanced nanophotonics at Texas A&M. The secret lies in these tiny devices called metajets. Assistant Professor Dr. Xiaofeng Lan and his team recently dropped a study in the journal Newton introducing these little tools. We're talking about micron-scale devices, literally smaller than the width of a human hair, that use lasers to lift and steer objects without zero physical contact. Imagine perfectly moving an object exactly where you want it to go just by shining a light on it. But you're probably wondering, how does a device the size of a hair actually catch light? Well, it's all about what they're made of, metasurfaces. These are ultra-thin materials engineered with incredibly tiny patterns. Think of it kind of like shaping a glass lens to focus sunlight, but executed on a ridiculously precise nanoscale level. The features on these surfaces are carefully designed in their shape, their orientation, and their placement to perfectly dictate how momentum transfers from the light directly to the object. Section 2. The ping-pong physics. Okay, let's explore the actual mechanics here. How does flashing a laser on a tiny patterned surface turn into a physical push? To explain this, Dr. Land brilliantly grounds a super advanced physics in an everyday analogy. He says it's like ping pong balls bouncing off a surface. Just like a ping pong ball physically taps a paddle and transfers energy, when light reflects off these metasurfaces, it transfers momentum. And that creates a small but highly measurable force that actually pushes the object forward. It's a really elegant, highly controlled three-step sequence. Step 1, the laser illuminates the metajet. Step 2, that light reflects off the carefully patterned metasurface. And Step 3, the momentum transfers, physically pushing the object. So it's illumination, reflection, and then targeted physical movement. Now, here is the absolute game changer: full three-dimensional maneuverability. The Texas A&M metajets demonstrate complete three-dimensional control, and to the team's knowledge, this is the very first demonstration of 3D maneuvering using this specific type of optical approach. So they aren't just pushing something in a straight line, they are steering it precisely through 3D space using absolutely nothing but light. To really appreciate how revolutionary this is, consider that conventional optical methods usually rely on altering or shaping the light beam itself to control an object. But these Texas A&M metajets, they completely flip the script. The control is built directly into the material itself. By baking that directional control straight into the nanoscale patterns of the metasurface, they're getting far more flexible force generation. Section 3. The global effort. To fully grasp the momentum of this field, let's zoom out and look at how institutions worldwide are tackling the complex physics of these light-induced forces. As we can see, Texas A&M is advancing the field with this new 3D maneuverability and fundamental physics framework, but it's a huge collaborative push. Over at Caltech, they're heavily focused on propulsion stability. The Rochester Institute of Technology is utilizing diffractive grating platforms, and across the pond, various European research groups are making major strides in related foundational physics. It's a massive global effort to harness how light interacts with the physical world. Section 4. Scaling up for space. So let's address the elephant in the room. How do we take a device smaller than a human hair and scale it into a system capable of actual spaceflight?
First, let's look at where they are right now. The doctoral students in Dr. Land's group who led this whole thing produced these devices at the Aggie Fab nanofabrication facility with support from TEES, the Texas A&M Engineering Experiment Station. To actually test them, they had to conduct experiments in a fluid environment. This was crucial because the fluid helped offset Earth's gravity, allowing them to clearly observe that light-driven motion.
And this is the real aha moment. The force depends on the power of the light, not the size of the device. This is exactly why scale isn't a barrier. Because the underlying physics dictate that force scales with optical power, the whole concept can seamlessly extend to much, much larger macroscopic systems. Basically, if you have sufficient optical power, the exact same principles driving a microscopic metajet could drive a full-scale spacecraft.
So what is the next step to actually prove this? Microgravity testing. The Texas A&M team is actively chasing external funding right now to get these metajets out of a fluid lab setup and into microgravity environments. Taking gravity out of the equation entirely will let them study the pure light-driven propulsion without Earth holding it back. The ripple effects of this research are already happening. Academically, they're already incorporating these light-induced forces into graduate coursework, which is naturally drumming up tons of undergraduate research interest. But the big picture impact? This heavily suggests a future of entirely fuel-free spacecraft. We're talking about moving and controlling interstellar probes without physical contact and without hauling thousands of pounds of combustible fuel. Based on everything we've gone through in this explainer today, it leaves us with one incredible paradigm-shifting question to ponder. Will our first interstellar spacecraft be fueled by absolutely nothing but light? From ping-pong physics to microgravity testing, they are laying the foundation right now. Thank you so much for joining me to explore this phenomenal breakthrough. And as always, keep questioning what's possible.